Have you ever seen that happen? Have you ever wondered why, when you take a balloon outside in the cold, it seems to lose all of its life, and then when you take it into a warm room, it reinflates itself? Well, the answer is in Charles' law. Charles' law is the second of the gas laws that we'll be studying during the gas chapter. Charles' law is all about volume and temperature. To be honest with you, why that balloon inflated was because it was sitting in a freezer. I took it out of the freezer, got it here as fast as I could, and very quickly it seemed to reinflate up to a larger volume. So Charles' law says that at a constant pressure, as temp increases, volume increases. So the pressure that the balloon was at in the freezer was really not much different than it was here in the classroom. So as the temperature increased, as that balloon warmed up, you saw the volume increase as well. Now, when you have two variables such as volume and temperature increase at the same time, we call that a directly proportional relationship. So as one value goes up, so does the other. And we can look at that in graphical form as well. So here you see a plot of Charles' law, and it shows on the y-axis volume, and it shows on the x-axis temperature. And you can see that as temperature increases, here's negative 300, negative 200, negative 100, 0, 100. We can also take a look at what's going on with the volume of a gas at a constant pressure. And you can see as temperature goes up, so does volume. That, in essence, is Charles' law. It's a directly proportional relationship. Much simpler looking example is here. Here we have a man standing on a canister of gas, on a container of gas, and underneath him you can see candles signifying heat. And as the heat, in the case of the first picture, there's half a candle there. There's not much of him rising, but in a full candle situation, the gas heats up underneath him. The particles are moving faster, so they strike the walls harder and more vigorously, causing the pressure to increase so much that he starts raising on the cylinder. And then in the third picture, we see two candles underneath this gas cylinder, which is taking him much higher. Gas particles are moving with greater velocity, they're striking the walls in greater number, and that is increasing the pressure. So what we see is that Charles did a number of experiments, and he showed that volume divided by temperature remains a constant value at fixed pressure. So using some semi-complicated mathematics, he initially came up with the equation V equals K times T, where K is a constant value. But to simplify it, he went ahead and he divided the volume by the temperature to equal the constant, and that allows us to utilize that equation in a lot of different ways. And that's where we're headed here. We're going to learn how to solve problems given conditions of gases that utilize volume and temp. So after using mathematics, he was able to change that V over T equals K to a gas that is in two different conditions. In the first condition, just like in Boyle's law, we use the number 1 to show what the gas was like at an initial set of conditions. There will then be information about that gas at a later set of conditions, and we show the number 2 as a subscript behind the V and the T to show that second set of conditions. So what we can say then is that V over 1, this is initial, and V with a 2 subscript would be final conditions. You're usually given 2 sets of conditions per scenario when you're given one of these gas problems. Okay, so let's take a look at Charles' rearrangement of the formula, and we'll put it to use with an example problem. And I'll go back to the helium balloon scenario. I have a helium balloon chilling in my freezer with 1.5 liters of helium inside. The temperature inside my freezer is 0 degrees Celsius. So what I want to do right now is I want to take some notes about these values and what they represent. So 1.5 liters, liters should give away the fact that we have a volume we're talking about. So this would be V1. The temperature is 0 degrees Celsius. That's going to be my T1, my initial temp. Reading on, it says, I take the balloon out and let it warm to room temperature at 23 degrees Celsius. What is my new volume? So 23 degrees Celsius is going to be my T2, my second temperature. And my volume that I'm looking for, V2, is unknown at this point. Now, you can also see down below, prediction popped up. You should also always do a prediction based on what you're given, and then when you're done with your calculations, see if it matches that prediction. So in this case here, I took a balloon out of my freezer, and you saw at the beginning what happened. The balloon just kind of expanded, and you could hear it crackling as it refilled the container it once was in. Or I should say initially was in full, put it in the freezer, it shrunk back down, took it back out, it came back out. So if I'm taking a balloon out of the freezer, my prediction is that my new volume is going to be bigger. So what do? Well, just like with Boyle's Law, what we're going to start with is a table of known values. We're always going to put one of these down when doing a gas law problem. So it's nothing more than you writing the variables and the numerical equivalents that you find in the written description of the problem. So V1 was 1.5 liters. I'm getting that from right up here. My temperature, my T1, was 0 degrees Celsius. Now, with temperatures, what you're going to want to get in the habit of doing is changing them to Kelvin temps. And to do that, we add 273 to our Celsius temps. So 0 plus 273 equals 273 K. It's that easy. With our V2, we said that is what we're trying to find, so I'm going to put a question mark there. And our T2 was 23 degrees Celsius, which again, we're going to add 273 to that to get our temperature in Kelvin, and that gives us 296 K. Now, we have 3 out of the 4 variables, which allows us to solve for the fourth. We mentioned that during Boyle's Law. If you have any 3, you can always find the fourth one using a little bit of algebra. But what we're going to do is we're going to set it up just like you see here in this little graphic of the equation. So we wind up having 1.5, and that's going to take the place of V1. So I'm going to put liters behind it. 273K is my T1, so that goes underneath it. I have an equal sign here. I have V2 on the top, and that's just going to stay as V2 because it's an unknown variable. And then underneath V2, my second temp is 296K. So how do we go about solving for the variable? Well, very easy. All we have to do is get rid of this 296, and then V2 will be isolated by itself and on top of the division line, exactly where we want it. So what we're going to do is we're going to take our 296K and multiply it by both sides, and that's going to allow us to cancel it out. So times 296K here, and over here as well, times 296K. Okay, and obviously that means it's going to be multiplied by what's on top of the line there. So here it cross cancels, and here now we have 296 times 1.5 divided by 273, which gives us V2. So after cranking that through on a calculator, I believe you wind up getting, and you can double check this yourself, 1.6 liters. Now, how do I know it's liters? Well, because here's a K on a top and here's a K underneath. Those cancel out. Wherever you see it twice, those units will cancel out. And then liters is the only unit left over, so 1.6 liters. Now, does that match with our prediction? We said it would grow, and it did. Not by much, by 0.1, but it did grow. So in the case here, I used some very simple ways to isolate the variable. Some of you guys may know it better this way, where if you have something underneath, all you really have to do is slide it up here to now join with the 1.5, and then you have 296 and 1.5 above this line, 273 below that line. It's the same thing mathematically. You wind up with the answer 1.6 both ways. Okay, so that's Charles' Law. Charles' Law again relates volume and temperature, and as the volume goes up, temperature goes up as well. Also, conversely, we could say as temperature goes down, volume goes down as well. So I hope that helps on Charles' Law. Good luck, study hard.